compressed into the rate part. Subsequently, every time a permutation is evaluated. And at the end, the digits is extracted also from the rate part, interleaved with permutation calls. So the sponge was originally introduced for hashing. For instance, the SHA-3 design follows the sponge mode. But there are also keyed applications of the sponge. One can, for instance, think of stream cipher encryption, where one sponges the key and the nonce to get some key stream, and this key stream can then be XORed with some message. One can also do some kind of blockwise streaming, where you sponge the key, the nonce, and some counter to get a counter key stream ki, which is then XORed with a message block. Another application of keyed sponges is authentication, where we want to design a MAC function. The original designers of the sponge suggested to use a MAC function as follows: so just concatenating the key and the message, and then sponging the input to get the MAC function. And the third application would be authenticated encryption, where we use a duplex mode. And this work is mainly concerned with authentication, and in more detail how to construct a MAC, or in fact a PRF, from the keyed sponge. And in literature we see two basic ways of doing so. One of them is essentially this one, and we see another way, and I will discuss both schemes. Starting with this one. This is the original keyed sponge as introduced by Bertoni et al. In this work we will call it the outer keyed sponge, and the reason for this is that the key gets XORed in the outer part. So what happens, the key is concatenated with the message. The key may be R bits long, it can be 2 R bits, 3 R bits, it may be any multiple of R bits long, and it's XORed into the rate part. And if you look at the picture, we see what happens. The parts of the wire that are red are the ones that are unknown by any user of the scheme, and they are unknown by any user of the scheme. That's relevant to see here. So this is the outer keyed sponge from Bertoni et al. 1 year later, Chang et al. Suggested to use what we call the inner keyed sponge. And in this case, the key is not anymore input via the rate part, but via the capacity part. So the capacity part right here, is initialized with the key. So in this case, the key is of length C bits. Note that we can equivalently describe the scheme as follows. So instead of initializing the state with the key, right here we XOR the key into the state, and then everywhere in between two primitive calls we XOR the key twice. So we can equivalently describe the inner keyed sponge as follows. So this is the exact same design. But if we now consider one XOR of the key, one primitive call, and one other XOR of the key, we consider this to be a block cipher. It's essentially just a low entropy Even-Mansour block cipher. Then the inner key sponge is equivalent to the classical sponge based on the Even-Mansour, based on the public primitive f, where the Even-Mansour is keyed via the C-bit key k. And we will use this description later in the paper, in the presentation, I'm sorry. And we consider both schemes, the security of both schemes, and in fact we consider the security in the following model. It's a PRF security model. So we consider any distinguisher. This distinguisher has access to either the keyed sponge or a random oracle, and the distinguisher tries to distinguish essentially both oracles. The distinguisher is also given access to the underlying primitive f. And the complexity of the distinguisher is counted by, first of all, the m, which is the online complexity. And m is essentially the total complexity of all queries the distinguisher makes to the construction. And n is the offline complexity, which is the number of primitive calls. So this is a security model, but let me first start by noting that Bertoni et al. Already considered the keyed sponge in this model. In more detail, they considered the scheme, and they proved that it achieves security up to m squared over 2 to the c plus 1, plus 2 times m times n over 2 to the c, plus n over 2 to the k. So there is already a bound. What's really the point of writing another proof? Well, there is actually quite a good reason for this, and the reason is that it turns out that there is a little flaw in the proof. In fact, lemma 1 doesn't tell you much right now. It's about the distance, and there is a small mistake in this distance, in the computation. The proof can be fixed, but this would result in an additional term in the security bound, and hence in a small security loss. The good thing, on the other hand, is that we use a different proof approach as the one used by Bertoni et al. This would lead to a better and easier to understand proof. In more detail, we consider a modular proof approach where we consider the inner key sponge or the outer key sponge, and we can view them as classical sponges based on Even-Mansur, based on the underlying primitive f, which we assume to be ideal. And using this approach, it turns out that we get, first of all, more compact, quite short and easy proofs, particularly due to this hybrid model. Secondly, we get better bounds than the one we saw before, partly due to Pathuran's H-coefficient technique. And finally, we get a more general bound because we use the principle of multiplicity. And the multiplicity is something typical to the sponge, so I will explain the idea. And consider here the picture of the outer key sponge again. And suppose right here, we see some value z0. So in one evaluation of the key sponge, there is this value z0 here. But it can also appear, for instance, here as input to a primitive. It can also be different construction calls that have this value z0. And it turns out that if some value z0 happens a lot of times, this will increase the advantage of the distinguisher. And to measure this, we use multiplicity. And the multiplicities are roughly defined as follows. So the forward multiplicity, for the forward multiplicity, we consider any possible value z0, and we count all f evaluations for which the rate part at the input equals z0, and we maximize over all possible z0. Similarly, for the backward multiplicity, we look at z1, and we consider all primitive calls that have a rate part at the output. So I told you this multiplicity is closely related to state recovery. One basic observation on this multiplicity is, first of all, that both forward and backward multiplicity are at most m. This is obvious because the total complexity is m. On the other hand, it's clear to see that they are at least m over 2 to the r, which is simply by the pigeonhole principle. And now it turns out that in a general case, where an attacker has the maximal power, it can make sure that these multiplicities are close to this upper bound, are close to m. But on the other hand, if we consider a keyed sponge with a unique nonce, for instance, the attacker is much more restricted, and it turns out that one can actually prove that these multiplicities are very close to the lower bound. And we will use this later in the presentation. So let's first go to the schemes and the new security bounds. Starting with the inner keyed sponge. Recall that the inner key sponge can equivalently be described as follows, where we have this Even-Mansur block cipher using the key k. And the first step we perform is we simply replace this block cipher by a random secret permutation pi. So we replace this block cipher by pi, which means that the security, the distance between the original inner key sponge and the random oracle, is upper bounded by the distance between the sponge based on a secret permutation and the random oracle, plus, of course, the security at which this block cipher behaves like a random primitive. And we consider these two terms separately. So we consider these two terms separately. Starting with the first one, first note that both the sponge based on a secret permutation pi and the random oracle are independent of this function f. So we can just as well forget about this. And if we do so, we see that this is just a very simplified case of the indifferentiability bound. So we can, of course, apply the indifferentiability bound of the sponge. Note that this is quite generous. One may be able to do better, but this is quite an easy observation, and in fact, this bound will be enough. So this is just the indifferentiability, this is part one. Part two is the distance, essentially from the Even-Mansur cipher, the distance from the Even-Mansur cipher to a random permutation pi. So this is essentially just the PRP security of Even-Mansur. Quite some proofs of this already exist. The one we derive in this work is slightly more general because we use the principle of multiplicity. And using these multiplicities and Pathuran's technique, we find that this term is bounded by the forward multiplicity plus the backward multiplicity times n over 2 to the c. So far for the inner keyed sponge. Later I will give an interpretation for the bounds. Let's first go to the outer keyed sponge. And the outer key sponge is more technical, and the reason for this is that the key is XORed into the rate part, but the key may consist of a multiple of blocks. So the key may be XORed in 1, 2, 3, 4, at 5 places, for instance. So the proof idea I will sketch here considers this general case, but in the picture, the key is only one block. And we denote the capacity value after the compression of the key by L right here. And of course this value L is secret. Any person that uses the scheme doesn't know L. But we can still, in our mind, we XOR this key L into the function twice. So everywhere in between two primitives, we XOR the key L twice. So this is just an equivalent description of the scheme. However, if you look right here, the state was L, we XOR L, so this is just as well, we can just as well just initialize the state, the capacity part of the state. And now we can do the same trick. So we again see this even Monsieur thing appearing, but now with a subkey L, where L is key derived. So we have this key derivation function that gives us value L, and using this L, we use the even Monsieur. And then we get the security of the outer key sponge is essentially the security of the sponge using the block cipher, using the primitive f, where the block cipher gets its input the secret key L, which is derived using the primitive f. And this particular thing makes it a little bit more technical to understand it, but the first step is still the same as before. We replace this block cipher by a random permutation, and we add the rightmost bound, which essentially measures how good this block cipher behaves like a random permutation. Okay, again, we consider the bounds separately. The first one is as before, we bound it by the indifferentiability of the sponge. The second one is more technical, and the reason is that this subkey L, the key derivation function and the block cipher use the same underlying primitive f. And in fact, there turn out to be difficulties if, for instance, one primitive call in the key derivation function is also made by the block cipher. So now we make a distinction essentially between whether or not there is a collision in these calls. So first of all, we show that if all primitive calls in the key derivation function are unique, then we get mostly the same bound, the one we saw before, except for a factor 2. On the other hand, it turns out that one of these primitive calls collides with another call to the primitive with essentially these two terms, this bound. The first one, this one corresponds to the probability that the attacker just guesses the key directly. And the second one corresponds to the probability that the attacker guesses one of the state values corresponding to the key derivation function. So this is the outer key sponge bound. And before proceeding, let me go to an interpretation of these bounds. So what we see is that the dominating terms in both the bounds, so for the inner key and the outer key sponge, the dominating term is m squared over 2 to the c plus 2 times the forward plus backward multiplicity times n over 2 to the c plus n over 2 to the k. Where m is the online complexity, mu forward and mu backward are the multiplicities which depend on the online complexity, and n is the offline complexity. However, note in practice that one may be able to bound the online complexity. One can, for instance, say that as long as the online complexity m is at most 2 to the alpha, and the forward plus backward multiplicity are at most 2 to the beta, so this beta moves for some reason, I don't know why. Beta should be a little bit more to the right. But, so as long as this is the case, one can show that the real security, so the time complexity should be at most, the beta moved again, 2 to the power c minus beta minus 1, and the minimum of this term, and 2 to the k. So what's the idea essentially is that if the online complexity exceeds this bound, one may, for instance, rekey, and the game starts over. And this shows that we have this bound on the offline complexity. The question now is, what is this value beta? Beta is, of course, related to alpha. And this brings me back to the multiplicities, because this beta comes from the second fraction in this bound. And using basic probability, we can bound the second fraction as follows. So we can say that this fraction is at most 2 times multiplicity forward star plus multiplicity backward star times n over 2 to the c, unless one of the multiplicities exceeds these bounds, which should happen with a small probability. And now in the general case, one sees that the forward multiplicity will be close to n, because the attacker has full control over the rate part. On the other hand, the backward multiplicity will be close to the lower bound, m over 2 to the r. And in fact, one can prove that the backward multiplicity will be at most a small thing times the maximum of 1 and m over 2 to the r, except with a small probability. And using this, we get a time complexity of 2 to the power c minus alpha minus 1, as long as the online complexity is at most 2 to the alpha. Now for a constraint case, in a constraint case, one can actually prove something similar. In the constraint case, if we have a unique nonce, for instance, both multiplicities are close to the lower bound, and we can do the same trick, and we see that the bound essentially implies a time complexity of a minimum of 2 to the power c minus 2 and 2 to the power r plus c minus alpha minus 2. So we have an additional term here because it depends on whether or not m is greater or larger than 2 to the r. And if you see some concrete examples, we see the bounds as follows. So the first row is the general bounds. The second row has a rate of 40 capacity of 160. This is, for instance, the case of the sponge with a 200-bit state. It's also used in the primates design. And one can then see that the bound imply that if the data complexity is at most 2 to the 79, you get a time complexity of at most 2 to the 80. If you additionally use a unique nonce, the time complexity increases to 2 to the power 119. And similarly, for the second case, where the rate is larger than the capacity, the second case corresponds to the Kiak design. So this was about the single setting. In the work, we also consider the multi-target setting. And in the multi-target setting, we essentially consider the case where an attacker tries to attack multiple instantiations of the key sponge. This is, for instance, interesting when many different users use the scheme for many keys. And it's particularly interesting to analyze because it may be the case that the scheme completely breaks down if one of the instances gets broken. And we also analyzed the results to the multi-target security case. First of all, we generalized the model. So we consider a distinguisher who has now access to either n keyed sponges or n random oracles. And the online complexity m is then divided into these sponges. Here, to be clear, the keys are assumed to be independent. And I will not go over the proof idea. I will just explain what happens for the proofs. And it turns out that there are some technicalities. These technicalities mainly arise for the analysis of the multi-target subkey even Mansur because we use this modular approach. But it turns out that apart from that, not much changes with respect to the bound. In fact, there may be, for instance, the case that there are collisions in between different keyed sponge evaluations, but this will all contribute to the same term. So originally we had m squared over 2 to the c. Now we get the indifferentiability bounds mh squared over 2 to the c for the individual keyed sponge instances. And we can get some cross-sponge inner collisions, which result in this bound. And together they contribute to the same old bound. For the multiplicities are simply counted again over all n instances at the same time. So there will be no extra term in this bound. There will be one extra term here, of course, because now we have n independent keys, so this increases the success probability of the attacker in guessing the key. So that's the end of my presentation. I would like to thank you for your attention.
Thank you, Bart. Any questions for Bart? We do have time. I'm afraid we have no questions, so you got away with it. Okay, so thank you very much.